In lab number 4, we're going to begin a series of videos on OSPF, Open Shortest Path First. We will introduce you to OSPF. We're going to see the concept of a DR, a designated router, and OSPF has various network types. We'll list the characteristics of each one, and we'll take a look at the syntax for basic OSPF configuration. We go out to our live topology and we'll set up basic OSPF. Then we want to influence the election of a designated router. So what we're going to do, we're going to set up the IP OSPF priority for an interface, and then we're going to verify that configuration.
Let's begin by reviewing some of the fundamentals of OSPF, which stands for Open Shortest Path First. It is a linked state routing protocol, and the way it does its shortest path calculation is via a mathematical algorithm called the Dijkstra algorithm. You see, after a router receives linked state advertisements, or LSAs, it can then use that Dijkstra algorithm to determine the shortest path to any destination network that it knows how to reach. And since we have these LSAs, these linked state advertisements that are being used to educate routers about the network topology, in a larger network, to constrain where these LSAs will be flooded, we might want to carve that larger network up into different areas. If we do that, we're going to have a backbone area, known as Area 0, that all of the other areas have to connect to. Everybody has to have connectivity back to Area 0 as the backbone area. If we just had a single area, most people still use Area 0 as the number of that single area, but it doesn't have to be with a single area. But if we have more than one area, we do have to have an Area 0, and everyone else has to connect back to that Area 0. And by subdividing the network into these areas, one of the big advantages we have is we're constraining the flooding of those LSAs to an area. We talked about the metric of EIGRP in the last lab, and the metric of RIP in the previous lab. What is the metric of OSPF? OSPF uses a metric called cost, but cost, at its essence, is really a function of bandwidth. Let's see how this works. To calculate the cost of a particular route, we take 10 raised to the power of 8, in other words 100 million, and we divide by the link bandwidth in kilobits per second. Next, consider the concept of a DR, a designated router. A designated router allows us on a multi-access network like an Ethernet network to have one router that's designated as the router to which all other routers should form adjacencies. This prevents every single router from having to form an adjacency with every other router on the network. In the example on screen, notice we have R1 that wishes to serve as a designated router. Instead of R2 having an adjacency with R3 and R4 and R1 and having a complete full mesh throughout all of these routers, what we can do is have all of the routers form an adjacency with router R1. That's acting as our designated router. We could also, by the way, have a backup designated router, and routers would form an adjacency with that BDR as well. But how does a router get to be a DR? How does it get to be a designated router? A designated router is elected by a router priority. We can associate an OSPF priority with an interface, and the higher the priority, the more preferable that interface on that multi-access network. If the routers have equal priorities, or maybe we just did not configure priorities for the router interfaces, the DR is automatically going to be elected by choosing the router on that segment that has the highest router ID. And the router ID is determined by the IP address of that router's loopback interface, or if we had no loopback interface, it would be the highest IP address on that router. And something else that we need to understand when it comes to OSPF networks are the different OSPF network types. For example, there is the broadcast network type. This might be on a multi-access link such as an Ethernet link. This is the default type for a LAN interface, by the way. Neighbors are going to automatically be discovered, and all of the routers belong to the same subnet. And on a broadcast network type, there is a designated router that is elected. On a non-broadcast network, which is the default on a frame relay serial interface, we are not going to dynamically learn our neighbors, so they might have to be statically configured. And all routers on this non-broadcast link, they are part of the same subnet, and there is a designated router that's elected. The point-to-point network type is the default type for a non-frame relay serial interface. Here, the routers at each end of the link, they form adjacencies with one another. We do not have a designated router. And each point-to-point link, which might be a point-to-point subinterface on a physical interface, each of those point-to-point links are on individual separate subnets. And finally, a point-to-multipoint network type. This is not a default network type for an interface, but it can be configured on any interface. Here, the neighbors are automatically determined, so we don't have to statically configure those. All routers, they are part of the same subnet, and we do not have a designated router. And in this lab, our Ethernet segments are going to have the broadcast network type, but we have a couple of sub-interfaces built on router R1 pointing out to our backbone routers of BB1 and BB2. Those are point-to-point sub-interfaces, so we're going to be using the point-to-point OSPF network type for those links. In fact, let's go out right now and remind ourselves about the topology that we're working with. In our topology, router R1 and R2 are interconnected via a fast Ethernet link, it looks like. So that means we're going to dynamically elect a designated router on that link. It's going to default to the router that has the highest router ID, and the router ID is going to be the IP address of the loopback interface. So router R2 seems to be a strong contender for the designated router, but we want to illustrate how we can manipulate that. What we want to do, we want to go in this lab and influence router R1 to become the designated router. We can do that by telling R2's fast Ethernet 0/0 interface that its IP OSPF priority is 0. We're eliminating it from consideration in a DR election. Also notice between R1 and BB1 and BB2, we have point-to-point frame relay PVCs. We're going to be using the point-to-point OSPF network type, in other words. Let's check out our syntax that we're going to be using. We're going to say in global configuration mode, router, OSPF, and then we give a locally significant process ID. And by locally significant, I mean that the process ID I give on one router doesn't have to be the same process ID that I give on its adjacent router. However, remember with EIGRP we had the concept of autonomous system numbers where our neighboring routers had to have the same autonomous system number. That's not the case with the process ID, as we'll see. We can then go in to router configuration mode and start specifying the networks that we wish to advertise via OSPF. We say network, give the IP address of the network, specify a wildcard mask, then follow that up with the area that this network is going to participate in and the number for that area. In this lab, we have a single area, so the area is going to be 0. And I want to show you a couple of shortcuts that we can use with that network command in this lab. And finally, we said we wanted to go into the fast Ethernet 0/0 interface of router R2 and convince that interface to never be a contender to be elected as the designated router. We can do that with the IP OSPF priority 0 command. Well, that's the theory. Let's go out now and take a look at the configuration. Let's begin our configuration on router R2. We begin by enabling OSPF on the router. We say router, OSPF, and we give a locally significant process ID. I say locally significant because this number, I used a 1, it does not have to match the process ID of any of our neighboring routers. It's only locally significant. Now we can start educating the OSPF process about the networks that are directly attached to R2 that we want to advertise via OSPF. We use the network command to do so. We say network, and let's advertise the 10.1.2.0 network. Notice it has a 24-bit subnet mask. However, the syntax for the network command says that we should issue a wildcard mask. The corresponding wildcard mask would be 0.0.0.255, and we say we want to be a member of Area 0. This interface is part of Area 0. Next, let me show you a shortcut. Even though the syntax calls for the use of a wildcard mask, check this out. What if we did this? What if we said network 192.168.1.0, notice we have a 30-bit subnet mask. What if, Instead of giving the actual wildcard mask, what if we maybe forgot and gave the subnet mask? What would happen? Well, let's try. Let's say 255.255.255.252. That's the subnet mask, not the wildcard mask. What's going to happen? Well, we'll see in a moment. Let's go ahead and say we're a member of Area 0, and then I will appropriately enter the network command for our loopback interface, 2.2.2.2, with a wildcard mask of 0.0.0.0, also a member of Area 0. What I wanted to show you is how the iOS can really help us out. We could enter the subnet mask and have the iOS automatically convert that into the corresponding wildcard mask. Let me show you. Let's do a show run and see what happened. If we take a look at our router configuration, let's scroll back up. If you take a look at the router configuration, look at this. I did not enter 0.0.0.3, did I? No, I entered 255.255.255.252. Huh, interesting. The iOS automatically converted for us. Excellent. Well, I think we're ready to move over to router R1 now. And on router R1, we want all of its interfaces to be members of Area 0. Let me show you yet another shortcut. We start the OSPF routing process, and because I want all of the interfaces to belong to Area 0, I could simply say network 0.0.0.0, 255.255.255.255, Area 0. And that's it. One network statement just accommodated for all four interfaces that I would have otherwise had to have configured manually. Big time saver. Next, let's move over to router BB1. We'll use the same strategy here. We say router, OSPF, 1, network, 0.0.0.0, 255.255.255.255, all interfaces participating in Area 0. We're finished on BB1. Next up, BB2, router, OSPF, process ID 1. Even though I made all the process IDs match, by the way, I didn't have to. I just wanted to be consistent, but remember, these are locally significant process IDs. Let's use that shortcut again. Let's say network 0.0.0.0, 255.255.255.255, area 0, and we're done. Let's move over to router R1 right now and see how our network is looking. Are we seeing all the routes? Exactly what neighboring routers is R1 aware of? Let's check it out. Over on router R1, we can say show IP OSPF neighbor. And we see that we have three neighbors. The neighbor IDs are the IP addresses of the loopback interfaces of the various routers. Something interesting to note, the state of this neighborship is full with router BB2 and with router BB1, but notice that there is no DR. There's no DR or BDR or DR other specified. The reason is these are point-to-point networks, and you might remember that the point-to-point network type does not require us to configure our neighbors because we did not do that. However, a DR is not elected. Conversely, the link between router R1 and R2 over this Ethernet segment, it is a multi-access broadcast network. So we do have a designated router, and we see that our neighbor is that designated router. We can get more information about that, by the way. We could say show IP OSPF interface fast Ethernet 0/0, and it tells us very clearly that the network type is broadcast. We see that our router ID is 1.1.1.1. We see that the designated router is 2.2.2.2, and it looks like we're the BDR, we're the backup designated router. What about those links going up to the backbone? Let's do a show IP OSPF interface serial 0/0.1, and we see that the network type is point-to-point. That's the reason that we do not have a DR for that link, and that's the reason we did not have to explicitly configure our neighbor. And just for completion's sake, let's say show IP OSPF interface serial 0/0.2 going up to BB2, and This is also a point-to-point network type. Let's check out the routing table. If we do a show IP route, notice that not only have we learned networks from all over the network, but the 10.network address space, notice that we have specific subnet information for the 10.1.2.0 network as well as the 10.1.1.0 network. That was not the case, you might recall, with EIGRP and RIP. Those both summarized those subnets into the 10. Address space by default. That's not the case, however, with OSPF. And the one thing that we might want to change at this point to meet our lab objective, we said that we wanted R1 to be our designated router. We do not want R2 to participate in that designated router election. Here's what we might do. Let's go over to router R2 and let's go into the interface for that broadcast network, Fast Ethernet 0/0. So let's go into interface Fast Ethernet 0/0 and we can give this command. We can say IP OSPF priority 0. That's going to prevent that interface from participating in this DR election. To make this take effect really quickly, here's what we could do. We could do a shutdown on this interface. Let's do a shutdown, followed by a no shutdown. Now, if we look at our neighbor listing, we can say show IP OSPF neighbor, and we see that now network ID 1.1.1.1 is the DR. We can further confirm that by saying show IP OSPF interface Fast Ethernet 0/0, and we see that yes indeed, now that we've adjusted that interface's OSPF priority, the designated router is now 1.1.1.1. I wonder how router R2 appears from the perspective of R1 now. Let's go find out. Let's go over to R1 and reissue the command show IP OSPF neighbor. And now notice that instead of saying that router 2 is a DR or a BDR, it now says it's DR other. It is not a candidate to become the designated router. Let's wrap this lab up by making sure that we have full reachability to all the routers in the network. From R1, let's do a series of pings. Let's ping 1.1.1.1. Success. Let's ping router R2 at 2.2.2.2. And let's ping 3.3.3.3. That's our backbone router, BB1. And let's ping BB2 at 4.4.4.4. Success. We have full reachability. We have influenced router R1 to become the designated router, and because we're dealing with the broadcast and point-to-point network types, there was no need for us to statically configure our OSPF neighbors. And since we've already demonstrated the saving of the running configuration to the startup configuration in previous labs, we won't take the time to do that here, and that's going to wrap up our single area OSPF configuration. In this lab, we considered the configuration of OSPF with a single area. We saw a couple of shortcuts for issuing the network command, where we didn't necessarily have to specify a wildcard mask. We could specify a subnet mask instead, and the iOS would help us out by automatically doing that conversion for us. And also, we saw that we could say network 0.0.0.0 space 255.255.255.255, followed by area and the area number, and that would make all of the attached networks on a router be advertised as members of that area. Coming up in our next lab, we're going to stay with OSPF, but we're going to expand our discussion a bit. We're going to take a look at multiple areas, where we have areas beyond just area 0. We're also going to illustrate the necessity for having every other area connect back to the backbone area, and we will take a look at a different OSPF network type, the non-broadcast type. which is the default on a frame relay serial interface, and we will see that neighbors need to be explicitly configured for that non-broadcast network type.